This one also start record. So basically, we have already, okay, we start. Okay, basically we have already finished discussing up to example 2.1, as you can see here, which is we have already discussed on the ideal transformer in our previous lesson. So this is the 5th week of lecture out of 14 overall that we have. So in this 5th week, we are still in the topic 2, but today we are going to move on to theory and operation of real single phase transformer. So we will be discussing on this section from today, and hopefully within this week, which is week 5, we will finish finish discussing on the topic 2, okay, which is transformer. So I think all of you already know that I have already posted the quiz 1 questions for you to answer, which is the online quiz. Just a simple question, which is could be level 2 of knowledge, up to level 2 of knowledge, which is related, which is multiple choice questions related to topic 1. And the time given for you to answer is 60 minutes. And I think some of you have already have already answered the quiz question that I've given. As I can see from here, 10 attempts, just 10 of you. I think more than 80% of you have already answered this quiz 1 question. So the due date for this quiz is up to 8th of November, up to today. Today is the due date of this quiz. And also, I have also given the exercise for you guys to answer the tutorial 1.4 and 1.5. And then I think all of the students have submitted this exercise, this tutorial exercise. This one has been released quite, I think, in week 3, I guess, week 3 or week 4, I'm not sure. So I will be checking on all of the submission that you have made. Then I will make sure that I will return it to you for tutorial 1.4 and 1.5. I will do some markings on it, right? Okay. So I think that's all about the e-learning system. And then also in the WhatsApp group, I have shared lecture notes related to section 2.4, which is theory and operation of real single phase transformer. So my handwritings has been shared with you, which is lecture notes that I have written last night. Then I have shared with you for reference, for you to make it as a reference, but make sure that, as I advise all of you, like before, you have to write your own, like your own notes. Yeah, you cannot depend on others' note. Make sure that you write your own notes. Okay. So I think you can just refer to that notes that I've given to you, and at the same time try to write your own notes. So let's start. So actually, any problem? Forgot to mute. Okay. So, okay, we start. Okay, ideal transformer. So far, before that, we have discussed in the previous lesson about ideal transformer. So in ideal transformer, we assume that some losses are neglect, meaning that we don't consider losses like hysteresis, eddy current, leakage, leakage impedances. We don't consider that. So we assume that that transformer construction was something like perfect, in the perfect condition with no losses at all. So that's that sort of thing we call it as the ideal transformer. But in real world, there is no such a construction that we can make a ideal transformer. There must be some losses in terms of hysteresis losses and also eddy current losses, leakage conductances, leakage inductances. So in this case, in this section in 2.4, now we are discussing on the operation, theory and operation of the real single phase transformer. This one is real transformer, which is the transformer that considers losses, that considers losses. So as you can see here in my notes, also I have written here, the ideal transformer is assumed as no losses. But for real transformer, we consider loss calculation, but basically not all of the losses we can consider because there are some other complicated system in the transformer we cannot do in terms of calculation. Maybe we have to do the experiment. So in this assumption, we consider loss calculation, but we still made some assumption. Okay, we still made some assumption. So in this case, just have a look at this figure at your side, which is in my lecture notes that I have written here. Okay, so we have a transformer core here with windings at the left hand side. As I can see from here, it's left hand side. Then we supply it with current at the primary, which is IP, and then this terminal at the primary is supplied by voltage of VP. Then the number of turns is NP. Okay, so the other side, which is at the secondary, you see that the number of turns of NS, and this is the open terminal. But as we can see at the bottom here, the transformer action. What does it mean by the transformer action? As stated at the bottom here, a time-changing magnetic field induces a voltage in a coil of wire if it passes through that wire. So once we supply the voltage at the primary side here, okay, supply the voltage and the current will be supplied through these windings or coil. So it will induce the flux that will be flowing inside this core, and then this flux will be passing through another coil, another windings at the secondary. So we have the time-changing flux, time-changing flux at the secondary. So what happened is the voltage will be induced. So this Vs is actually the voltage that has been induced because of the time-changing flux that occurs at the secondary or this winding lah, the secondary winding of the transformer, which is at the secondary winding we have ns number of turns, right? Okay, so from here we can say that for n number of turns, now we are going to discuss on how to do the calculation at the primary. Okay, so for the n number of turns, we assume that we have phi I for n number of turns, meaning that all n number of turns, which is turn number 1, turn number 2, turn number 3, so and so forth until n, we assume that all of the flux there is phi I, okay? for n number of turns. But for every turn, phi is not equal, meaning that for turn number 1, we have phi, right? But phi for second turn, which is turn number 2, is not the same as for phi at turn number 1. Maybe some other value of phi. So every turn is not perfectly done, which is at the factory, maybe there might be some something which is not perfect happens. Okay, so that makes the phi for every turn is not the same. So what we can see, what we can say in terms of calculation, in terms of mathematics here, we can say that phi 1 is not the same as phi 2. It's not also equals to phi 3. It's not the same as phi and so on, so and so forth until 5n. So all of the phi's in every coil, in every turns is not the same. Then, so what we do is we can take the average. Okay, if we have many phi's but not the same value, we can do this sum all of the phi's, okay, and then divided by n lah, because we want to get the average phi, right? So basically what we do is using this equation, okay, phi average, phi bar, equals to lambda, which is the flux linkages that we have already learned in our previous lesson. Lambda is flux linkages, which can be defined by this equation. So actually, lambda is actually the total number of phi's, meaning that we add all of the phi's. Okay, we add all of the phi 1 plus phi 2, phi 3, so and so on until 5n equals to lambda, which is the flux linkage. So we added all together phi, meaning that that one is flux linkages. So all of the phi, which is flux linkages, divided by n number of turns. Meaning that, for example, we have 100 turns. Let's say we have 100 turns here. So we added all together phi 1 plus phi 2 plus phi 3 plus until 500. And then we divide that by 100. So we get the phi average. So this phi average is the average phi at the primary side. We assume that this phi average is phi at the primary side. So we added over all the phi passing through that turns of the coil. So this figure is drawn similar way to explain about each of the phi which is not same, and we assume that this phi is actually in the same direction and also magnitude, meaning that the vector of this phi is in the same direction, which is vector of this phi is the same. Okay, as you can see, as it has been drawn here, phi 1, the vector of phi 1 is upward condition, right? Phi 2 similarly to the upward, and also phi 3 upward, and so forth. So we make assumption something like this. Because if we apply current starting from top, we can do the right hand curl. Okay, we do the right hand curl, and then our thumb is actually pointing toward the direction of phi. Okay, so upward, this phi will be moving upward, which is in this case, as you can see at the primary turns here, phi is moving upward and then rotate following the clockwise direction, and then pass through the NS, which is turns at the secondary. Okay, so sort of thing about transformer. So here we can use the formula based on Faraday's law, which is induced voltage. Okay, induced voltage at the other turns, induced voltage, basically induced voltage because of flux changing in this turn. So this induced voltage, is it the same as the voltage here? Let's see. Okay, so induced voltage by Faraday's law, induced voltage is N times the rate of change of phi, which is, in this case, we consider average phi because we are talking about transformer with losses. Okay, we are talking about real single phase transformer. That is why we consider it as d phi bar dt, which is taking into account the different value of phi that we have here. Okay, so we get the average and d phi bar over dt for the induced voltage induced inside the turns according to Faraday's law. And then we can assume that actually the induced voltage inside this coil, is basically the same as the supplied voltage, which is VPT. So we assume that this induced voltage, because of the varying flux inside the turns at primary windings, is the same as the applied voltage at the primary windings. So we can just apply this Faraday's law, which is induced voltage is equals to Vp equals to Np d phi over dt. I'm going to call it as d phi, but you have to understand that phi is actually the average phi, right? Not the phi which is the normal phi that we have been discussed before in ideal transformer. So from this equation, we can see that Vp is directly proportional to the phi bar. Vp is directly proportional to average flux. So we can assume that phi bar is directly proportional to V. So in this case, since we do that assumption, okay, since we did that assumption, as I said earlier, we are talking about real transformer, but we still made some assumption, right? So this is some of the assumption that we have made. Okay, so using this equation from the previous equation, we can rearrange this by assuming that Vp is directly proportional to phi bar. We can rearrange this equation, which is Vpt dt Np d phi. Then we further rearrange it until we get phi bar equals to 1 over Np integration of Vp. Okay, Vpt, actually we have dt here. So Vpt dt, yeah. Okay. So this phi, this is the formula for average phi, the induced at the primary turns, all right? So this phi will be traveling through this iron core. This phi will be traveling to this iron core, which is induced the voltage at the secondary part, okay? Induced voltage at the secondary part. So we have already passed this. We've got this one, right? In that explanation. Okay. So this phi will travel to the secondary part of the transformer and then will induce potential, which is voltage at the secondary. So we can say in this case, referring to this equation, that the average flux at primary winding is proportional to the voltage level at primary side divided by Np. So this is the translation to this mathematical equation. So basically, this average phi at the primary will be traveling through this iron core of the transformer up to the secondary part, which is later, okay, as you can see, which is later will be induced also the voltage at the secondary part of the transformer. Which will induce the voltage at the secondary part of the transformer. Okay, so that is about the voltage across the transformer. Up to here in this slide. Now we are going to talk about the still about voltage ratio across the transformer, but now we are discussing on the we are going to discuss on the flux leakage, which is in the real transformer. We have to consider some leakage that occurs in the within the core of the transformer. Basically, not all of the flux will be flowing inside the transformer. Some of them will be lost to the air, to the outside of the core. Okay. So as you can see clearly, as has been drawn in this notes, we have a primary part and the secondary part here. So the circle one, which is this one, is the mutual flux. Mutual flux that is passing through the iron core. And in addition to the mutual flux that we have here, we have also the leakage flux at the primary, denoted as phi LP, and also the leakage flux at the secondary, represented by phi LS, right? So you can imagine this figure. Basically, in real transformer, there'll be some leakage of the flux. Not the same as the ideal transformer. We assume that all of the flux will be flowing inside the core, which is 100% of the flux will be passing through the core and until it arrives at the secondary part. Okay, so we can say that the average flux at the primary is basically not only the mutual flux but also the flux. We consider the flux that has been leakage. So average flux at the primary is equals to mutual flux plus leakage flux at the primary. So how about the voltage? Voltage at the primary. Okay. How about the voltage at the primary? Still, we can use the same method, which is using the Faraday's law. Okay. So at the primary, if we apply Vp of voltage at the primary, we can say that this Vp is equals to mp d phi over dt, just using Faraday's law. Now this phi, we substitute this phi p average with this equation. Then we can just further calculate further extend the Faraday's law. We can further extend the Faraday's law until we get Vpt equals to induced voltage at the primary plus induced voltage at the primary, which is the leakage. So this one refers to the leakage potential. This one refers to the potential that has been induced, which is the majority of the voltage will induce EP actually. Okay, so we do the same way for the secondary part using Faraday's law again, which is we have at the secondary part. This is average flux at the primary, which is phi m plus phi LP. For the average flux at the secondary, it is phi m plus phi LS lah. Okay. still sharing the same mutual flux, but also added with the leakage flux at the secondary. So this is the equation for secondary part. We do the same thing as the primary part, all right, until we get this pattern, which is this part actually represents the potential because of the mutual flux. This is the potential because of the leakage flux. So we get the equation of Vs equals to this equation. So we do the comparison, which is EP equals to NP d phi m over dt. Okay, EP equals to d phi m over dt. And then we rearrange this equation, which is we get EP over NP equals to d phi m over dt, right? And this one, we compare with the secondary part, okay? This secondary part, okay, we get ES over NS. And then we do the same way, further calculate this real transformer assumption. We get the same thing, which is the ratio of induced voltage at the primary to the induced voltage at the secondary is equals to the ratio of the number of turns at the primary to the number of turns at the secondary, which is as a result, the ratio of NP over NS, we know that it is the turns ratio, which is, we name it as A. Okay, so NP over NS is A, which is the turns ratio of the primary turns by secondary turns. So in a well-designed transformer, we have reached this part actually. So in a well-designed transformer, basically we can say that most of the flux will be flowing inside the transformer core. Okay, there will be some minimal of the flux will be released to the air, will be out of the core, which is leakage. But the majority will be confining inside the core of the transformer. That is, we can say that using this expression, phi m is basically large enough compared to the phi leakage at primary. Okay, so similarly for the leakage at the secondary part, we can say that the mutual flux will be much more larger than the leakage flux at the secondary. So in that case, okay, we can say that this one for induced voltage, right? We can also say that the supplied voltage, which is supplied voltage, we are talking about the voltage we supply to the transformer, supplied voltage, and then voltage which is induced at the this terminal, this open terminal. Is basically we can do the same assumption. Vp over Vs equals to Np over Ns, which is equals to A, which is the, as you can see, the pattern where we where we describe on the real transformer is almost the same as the pattern of the equations that we discussed in the previous lesson of the ideal transformer, right? So basically, in explanation about real transformer, this is basically we end up with the same equation, almost the same equation to the ideal transformer. All right. The difference is in terms of how we elaborate or how we extend the calculation considering the leakages of the inductances, flux leakage, and also the losses. losses, other losses that occurs in the transformer. We will be talking about another losses in the next slides. So now, losses in terms of magnetizing and now we are talking about the current in real transformer. Just now, in the previous slide, we've been talking about voltage. Now, how about the current, which is in this section, we'll be discussing further on the current inside the transformer, which is current also occurs losses in terms of hysteresis loss and also eddy current loss. So in this section, we will continue to discuss on the current that is flowing inside the turns of the transformer. In my lecture notes, as you can see, I have drawn another figure that shows clearly. Before we move on to the current, discussing on the current in the real transformer, just a little bit explanation about this figure. As you can see, this is the figure that I have adopted from Chapman's book. Okay, I have redrawn it. So as you can see, some of the flux will be leakage inside and then outside of the transformer core. Okay, so but basically we name it as the leakage flux at the primary phi LP for this one, and also for the other side of secondary part, we name it as phi LS, which is the secondary leakage flux at the secondary turns, right? This figure is adopted from Chapman's, and here we can use the right hand curl to define the vector or direction of the phi. As you can see, the direction of the phi at the primary side is to upward and then turns following the clockwise direction. And then similarly for at the secondary part, as you can see, if we use the right hand rule here, it is actually our thumb is pointing to the downward. That so phi is pushing from this side, also pushing to the downward at this side, right? So meaning that the flow of flux is clockwise direction. So the flow of flux is clockwise direction in this case. So if you want to make this transformer, which is nearly a perfect transformer, we can do it. We can just do it at the factory. We can never do this, but if we do it carefully, and then we try to make a perfect transformer, meaning that we minimize the flood leakage, right? So when we minimize the flood leakage nearly zero, meaning that we achieve we are close to the ideal transformer. But in real world, we cannot make an ideal transformer. There will be some losses. So we are going to discuss now on the magnetizing current in real transformer. Okay, the magnetizing current, we use the symbol of IM, which refers to the magnetizing current. The current that we supply to the primary core, primary windings of the transformer that will cause the induced voltage at the primary side. So this is what we call as the magnetizing current, which is the majority of the current. Okay, the majority of the current supplied by the voltage Vp is the magnetizing current. But not only magnetizing current that we are supplying, because we have to consider another current, which is the term used as IH plus E here, which refers to current due to the hysteresis and also eddy current. So this current is actually the core loss current. Okay, so in this case, for the current that is supplied to the core of the transformer can be divided into two. The first one is magnetizing current, And then the second one is the core loss current. Okay, so we can use the expression of F, which is MMF equals to NI. As you can see in your PDF slides here, F equals to NI equals to phi R. So F is analogous to, remember, for the electric circuit, F is analogous to voltage potential, right? Which is equals to number of turns times current that we supply. And also equals to phi R, which is phi is analogous to current that is flowing in the wire for the electric circuit. And then R is reluctance. And for R is not so confusing because it used the same symbol, which is R for reluctance, and in electric circuit we represent R for resistance, right? Okay, so we can rearrange this equation to represent it in terms of I, which is I equals to phi R over N. So in this car, okay, so basically, okay, what happened when the voltage applied to a transformer? Okay, when we apply the voltage to the transformer, we can assume that, let's say this is the voltage that we apply, which is Vpt equals to Vm cosine omega t. So this is the cost function, right? The cost function. So this is the voltage. This is the voltage. Vpt is voltage at primary. Voltage applied. Apply at primary. So we apply voltage, which is cost function. And this voltage, we know that this voltage will produce phi, which is the flux inside the coil. Okay. So we can say that the phi is now sine function. As you can see in this equation, phi is sine function. I just can, as you can see, I can redraw it like this. When Vp is at 0, phi p is at the maximum, at the maximum point. And then also sine function, something like that. So this is phi p average, which is Vm over np omega sine omega t. So as you can see, we apply sine function of voltage. What happened inside the coil is the average phi that occurs inside the coil is sine function. Why do we get the sine function? Why do we get the sine function? Okay, this is explained in this notes. As you can see in this notes, okay, this one is from the voltage applied, Vp equals to Vm cosine omega t. We know that from our past discussion on the previous lesson, the average phi, as you can, okay, in page 3, the average phi is this equation, 1 over np integration of Vpt dt. So we can use that equation here. Can use that equation here to calculate the phi. Okay, phi that is induced at the primary of the transformer. Okay, using this equation, substitute Vp, okay, then we further calculate this until finally we get average phi at the primary is Vm over Np omega sine omega t. So this is just a simple calculus, which is if we integrate cosine, we will get 1 over cosine. If we integrate cosine omega t, if we integrate this, we do the integration. If we integrate cosine at, for example, we will get 1 over omega cosine omega, sorry, 1 over a cosine at. Okay, so I hope that you know on how to get this, right? You just do the integration, refer to the trigonometric, it's quite hard to pronounce. Trigonometric function. Let me just Google it for you. If you Google the
Google helps you search, view, see, find, play, learn, work and have fun.
cosine
What can I do for you?
integration, you don't have to do nothing to me. Just why should I do this? Don't tell me about it. And search, no, I don't need that. Okay. Go to image, and then you will see some of the functions. For example, in this one, if we integrate cosine ax dx, we will get sine ax over a. Okay. If we integrate sine ax, we will get negative cosine ax over a. So that sort of thing. We use this trigonometric function of cosine and sine to calculate this 5p bar. Okay, then we get, actually from cosine function we get the sine function. That is the explanation why we get this phi when we apply Vp. What happened is at the primary side we get the blue one, which is phi. This is average phi. Okay, we get average phi, which is sine function. So that sort of explanation about phi that is induced because of the voltage Vp. We supply voltage Vp again. Okay, the black one here, this is Vp, and then the induced flux, phi is sine function here. Okay, so then for the current, basically we can still using the same equation that we have learned in the previous lesson, which is phi equals to Ni equals to phi r. You can say that in this case, phi is proportional to the current. Current is proportional to the phi flux. Right? This is the explanation about magnetizing current. Okay, so basically the magnetizing current. So basically we are going to we are talking about the magnetizing current. In this case, what is the voltage applied? So basically just now, as we can see, that we can say that current is proportional to the flux. Current is proportional to the flux. Just now we estimate the average flux is this curve, right? We estimate average flux is this curve. So in real world, this is not, so this is flux, huh? This is flux. So this one is flux. This one is phi. That we can say this phi is actually directly proportional to the current. So in this case, is this what we call magnetizing current? Is it magnetizing current? In other words, is this actually the magnetizing current, which looks like the pure sinusoidal function like this? Is it correct that we can say this is phi, so which is directly proportional to the current, which we can also write it as I for this curve, which is phi curve. Huh? So is it actually the magnetizing current that we are talking about? Basically, in this explanation, in real world, this is not the magnetizing current. Actually, the magnetizing current that is supplied to the transformer, the curve is sine function, but it should look like this. Okay, the curve of the magnetizing current is still sine function, but it looks like this. It has some extreme 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 high frequency component, which is harmonics of the third order, fifth order, which is harmonics. So actually, the current function is not pure sine. It's not a fundamental sine function, but it's more to the high frequency harmonics, which is, if we do a plot, so if we refer again this initially we supply Vp, which is the red one. We supply Vp, we'll produce phi, which is sine function of phi. Okay, from here, how about this phi? This phi t, actually it will be like this lah. It will increase, and then after some time it will be saturated because of the permeability of that particular core of the magnet of the transformer. So it will be saturated here. So once it is saturated, it will be needed more current to be supplied to support, to compensate for this saturation. So that cause more losses occurs. So because of this saturated part, the curve here, okay, we will have to supply more current. If we plot this current, which is a bit of rotated, yeah. So because we want to make sure that the current the current axis is horizontal, the same as the current axis of this one. Okay, so if we plot current over time, the current is still sine function, but at this instant, at the peak of the current, it will producing more current in order to compensate for the saturation that occurs here. Okay, so as you can see, the current pattern will looks like this. Let me just search Google. In the Google, for the magnetizing current of the oscilloscope. Magnetizing current of the oscilloscope. So as you can see, like as you can see in this image, this is actually the current supplied to the transformer, which is not a pure sine function, but more to the sine function with harmonics. Harmonics. Similar to this one, we have different pattern of the current, but as you can see clearly, it contains harmonics. This is another example. From the oscilloscope, we can see that actually the current supplied to the transformer is not like a pure sine wave like this. It's not a pure sine wave like the flux inside, but it is more to something like this. Okay. So this is another figure that explain on how the magnetizing curve here, magnetizing characteristics of the flux here will influence the pattern of the current supplied to the transformer. Okay. So as you can see, flux variable in time, which is the pink one, but the current supplied to cause the flux of sine here, the pure sine flux, is something that looks like this, the red one. And this current, this pattern of current is actually contains harmonics. Actually contains the harmonics. Page action, insert page. So harmonics, harmonics, if we have this sort of pattern of current, okay, actually it contains a fundamental. This fundamental is at 550 hertz frequency, and we have it also contains this sort of pattern. For example, in this case, this is much more higher frequency, something like this. So this is higher frequency. Maybe third, for example, this one could be third harmonics of current. Okay, so we add together these two, we get this. Okay, so about the harmonics, I think you should go on previous studies related to the electronic circuits. For example, in inverter, what else? Energy conversion, energy converter studies. We'll be talking about harmonics. Harmonics current. If you Google harmonics current, you will see that this sort of image.
Here are some results from the web.
When I call Google, this Contana will be talking. All right. So this is harmonics. Okay. For example, we have the distorted wave, which is the yellow one here. So this distorted wave is actually the sum of the pure wave, pure sine wave, which is fundamental, plus the harmonics. Okay, the harmonics. So that sort of things. So actually in studies about harmonics, what we can feel is actually in transformer itself, we can say that this harmonic current will cause heat, that occurs inside the transformer. If we touch the body of the transformer, of course, we will feel heat, which is resultant from the harmonic current. Right? So that heat also contribute to loss in the transformer. Okay. So in this lecture notes also explains more about the characteristics of the magnetizing current that occurs inside the transformer. So what we can say about the magnetizing current of a transformer is, firstly, it is not a sinusoidal function of curve, which is it consists of fundamental plus higher frequency harmonics. So it is not pure sine, but more to the fundamental plus pure, which one? Fundamental plus higher harmonics current. And then frequency lag voltage at 90 degree. So as you can see, we get the sine function for the current, but for the voltage is cosine function, meaning that for the frequency, in terms of frequency of the current that's supplied to the transformer, it is actually lag the voltage about 90 degree. So that is why for the current is sine function, but for the voltage is cosine function, because cosine omega plus 90 degree is equals to sine omega, right? So number 3, at saturation, high frequency component will be extreme. So this is high frequency components of the magnetizing current during the saturation. Yes, during the saturation, the high frequency component will be extreme, which is at this part, which is much more high frequency compared to the other parts of the curve here, right? And then number 4, when peak flux reaches saturation point, small increase flux will need more current. So when peak flux, when this flux increase the saturation point somewhere here, more current will be required to compensate for the loss. Okay. All right. So other than the magnetizing current of the transformer, the second component of the current is called the core loss current, which is this one is much more related to the loss, loss of the transformer in terms of hysteresis loss and also eddy current loss. As you can see in this figure that I have drawn here, this is the normal pattern of flux produced inside the transformer. Okay, this is the normal pattern of flux produced inside the transformer. How about the current? As you can see, if the flux produced as a sinusoidal function here, as you can see, the sinusoidal function, sine function for flux, since you know that the eddy current, okay, eddy current, eddy current is d phi over dt. Okay, we have already seen this in our previous lesson. D phi over dt is eddy current. So if we do the d phi over dt, okay, we do the d phi over dt, which is differentiation of the phi. At this instant, at this peak of the sinusoidal flux here, d phi over dt, of course, this one is 0. So we can say that the loss, which is core loss current, the core loss current is also cosine function. But actually, it is not like this pure cosine function like this. Not a very smooth or very good cosine function like this, but it is more to the something like this at the bottom, as you can see. It also has some non-linear characteristic in terms of harmonics, which is, as you can see, the current pattern should look like this, which is much more, it's not a sawtooth signal, it's not a square wave signal, but something like trapezoidal or something like that. Okay, so it is flat on the top, and then still the sine function is flat on top and then flat at the bottom. Okay, So, but this one is in phase with the voltage applied. So we apply the voltage of sine function, sorry, the cosine function of voltage. The loss in terms of core loss current is also cosine function, right? So we get it like this. So similarly, if you, as you can see, this is the figure from Chapman's book. So we get the current of the core loss current of cosine voltage, cosine function. So we get the cosine function, but it is not a pure cosine function like the dot dot function here, but it is more to the something like the function that contains harmonics. So this is the current of due to the harmonics and also eddy current. So this is, we call it as the core loss current. Okay. So there are two functions of current, two types of currents supplied to the transformer. The first one is magnetizing current, which is something like this. So magnetizing current is sine function, but added with harmonics. Yeah? Okay, sine function added with harmonics here. And then another component is core loss current, which is the cosine function, which is similar to the voltage, but also contains harmonics. Huh? So IH plus E should look like this, and IM is like this, right? So finally, what we can say in terms of excitation current. So excitation current means that excitation current IEX ni, IEX here is actually IM plus IH plus E. Okay, so this is the excitation current. So this is VPT. So excitation current is actually what we can see in this figure is this pattern, this function plus this function, we call it as the excitation current. Okay. So what is next? Okay, so next we'll be moving on the current ratio of a transformer and the dot convention. This is more to the more formula that is actually described the same as the formula that we have discussed in the ideal transformer, but this one is considering the formula that taking into account the real transformer. Real transformer, we'll be talking about more on the losses. We consider this all of the losses, four types of losses here: copper loss, eddy current loss, hysteresis loss, and leakage flux loss. We represent this component in terms of inductance and also the resistance of the equivalent circuit of the transformer. So we'll be talking about this later. I think we'll have a break about 5 minutes before we continue. So this class will finish around 10. So that we will have another maybe around 40 minutes. Okay, and around 40 minutes. So we take a break about 5 minutes before we continue. So we continue. I hope you are still there in front of your computer. Okay. So we continue on this section, which is current ratio on a transformer and dot convention, which sounds similar to the previous lesson, just about the formula that we use in the transformer. But in this case, we consider the real transformer. Okay, that in this equation that we will compute, and then we will do the equivalent circuit later, is more to the something that considers some of the losses that occurs in the transformer. So we will represent some of the losses in terms of the equivalent circuit that represents, for example, the resistances, the impedances, inductances, okay, and then also resistance of the equivalent circuit. So, okay, we move on to the lecture notes, the notes that I have given to you. Current ratio of a transformer and dot convention. Dot convention. So we have discussed the very similar thing in our previous lesson related to ideal transformer, but this one is more focused on the real transformer. As you can see here in this figure, the same figure that I've redrawn it in my lecture notes. We have the transformer core, which is supplied by the current at the primary side. Okay, and then also the current at the secondary side will be induced. Okay, so in this example, we use the dot convention that represent the direction of the current flowing. For example, as you can see, we use the dot convention. If we place the dot here, meaning that at the primary side, the current will be flowing into the dot. Okay. At the secondary side, on the other hand, as you can see, if we place the dot here, meaning that this current is actually flowing out of the dot. So the tricky one here is about current. Okay, one current at the primary flowing into, one current at the secondary flowing out of. Okay, that is the tricky part about current. The voltage is the same. Okay, if we see the dot here, meaning that this is the plus of the plus. I mean the plus part of the voltage, which is the positive of the voltage induced. Okay. Similarly, for the secondary part also, if we see the dot here, meaning that we just put plus, then minus at the bottom. Okay. So the polarity of voltage is plus at the dot. Similarly for the secondary part also. Okay, so we use the similar notation to what we have found in the previous lesson related to the ideal transformer. So in real transformer also, we see Vp at the primary side. Okay, we supply by Vp, and then the current will be flowing inside this coil or in these turns, which is the number of turns represented by Np. And current at the primary side is denoted as IP. So the flux will be induced at the primary side and then turns into the flow of the flux of clockwise direction, as you can see in this handwriting lecture notes here. So phi will be moving clockwise direction. Okay. Passing through the number of turns, the turns of the primary side. Okay, in this case, we can say that for the primary side, the F, which is the MMF that produced at the primary side, we name it as FP. And then at the secondary side, we name it as FS. So this is the MMF. All right. So for this MMF, actually, we can calculate the F net, which is the net MMF of these two terms, right? F net equals to Fp plus negative Fs. Why negative? Okay, we'll explain later. So plus minus or negative Fs equals to phi R. So this is the normal magnetic circuit punya magnetic circuit the equation, the normal equation of the magnetic circuit, F phi R, F equals to phi R. But for this case, Fp plus negative Fs. Why negative? Because as you can see here, if we use the right hand curl to identify the MMF, okay, phi, okay, actually this phi from primary part will be flowing clockwise direction, but phi for the secondary part, actually if we do the right hand curl, phi s is flowing to that direction, right? If you if we do the right hand curl or right hand rule lah, sama, right hand curl, we can say that actually phi s is moving opposite to the original flow of the phi p. But in this case, F net, we are talking about F net, which is F net is actually, we consider F net is actually flowing clockwise direction, okay, in this case. So we assume that F net is flowing clockwise direction. That is why we use the negative here, which is, this is opposite, opposite direction. Actually, if we do the right hand curl, we can say that this is opposite direction at the secondary part. So we use this expression equals to phi r. Then we reach to Fp minus Fs lah, equals to 0. So in this case, why 0? Because in a well-designed transformer, R is equals to 0. In well-designed transformer, there will be no reluctance, no reluctance inside this transformer. So we can say that R equals to 0, phi R, which is R equals to 0. So this part is 0. So Fp minus Fs is 0. And then we can say that actually primary part of the MMF that is produced by this transformer is equals to the secondary part of the MMF. So we can further rearrange it because we know that F equals to Ni, right? From our previous lesson. So we can use NP IP equals to NSIS. Then we can further rearrange this to consider the what we call as the turns ratio. This is the turns ratio. Also, we have found this in our previous lesson as well. Turns ratio, when we rearrange this equation, we get the turns ratio in terms of NP divided by NS. Then we get IS over IP. And then we get the very similar equation to the ideal transformer. Similarly, for the real transformer also, we can use the same equation, which is IS equals to AIP, right? So A is IS over IP. But for A, for the voltage, is VP over VS. Okay. So how do we represent a transformer in the form of equivalent circuit? Okay, this one is the calculation in the previous explanation. We just skip on this one. So now in this theory and operation of real single phase transformer, I'm going to show you on how to represent the real transformer in terms of equivalence circuit that considers losses inside the transformer. As we can see so far, we have been talking about the ideal transformer. If we compare the ideal transformer and also the real transformer, we can say that there are some points that we can consider. For example, in ideal transformer, core does not have any hysteresis and eddy current loss. So we don't consider hysteresis and eddy current loss in ideal transformer. Okay. The second one, the magnetizing curve of an ideal transformer is similar to a step function, and the net MMF is 0. If you can have a check in the Chapman's book, page 85, similarly what I have been drawn here, I have drawn here for you. This is what it means by the magnetizing curve of an ideal transformer, which is similar to step function. So this is the step function, positive step function, negative step function. And the net MMF is 0, okay? Which is we add together the MMF, which is this is MMF, right? Positive plus negative MMF is 0. Net MMF is 0. This is what we consider, we assume in the ideal transformer. Okay. Number 3, flux in ideal transformer stays in the core, hence leakage flux is 0. We don't consider the leakage flux. We assume that all of the flux, 100% of the flux will be confined in the core, will be flowing in the core, so there will be no leakage for the ideal transformer. That sort of thing in the ideal transformer. And then number 4, what we assume in the ideal transformer is the resistance of winding in the ideal transformer is 0. So we don't consider the resistance of the, let's say, for example, we use the copper wire to do the windings. Basically, inside the copper wire, it has some resistance. Okay, in real world, in actual condition of the copper wire, it should have some resistance in it. But in ideal transformer, we don't consider the resistance that available in the wire, which is copper wire. Okay, in this case, so we don't consider, as number 4 says, we actually don't consider the resistance of winding. Okay, we don't consider the resistance of the winding in the ideal transformer. Okay, so when we talk about the equivalent circuit of a real transformer, there are few things. First, that we would like that we will consider. All right, few things that we will consider in the real transformer equivalent circuit. So we consider all of these 4 types of losses in the real transformer. So we take into account the first one, which is copper loss. What is copper loss? Which is actually the normal resistive loss, which is I square R. So this resistive heating losses in the primary and secondary winding of the transformer. Because we use the copper wire, okay? The wire is made of copper. We do the windings at the primary side and the secondary side. There will be some losses inside the copper wire. This is what we call as copper loss. That will cause heating. That will cause some sort of heating inside the transformer. Okay. The second one, we consider the eddy current loss. Okay. The second one is eddy current loss. In your PDF slides, is number 2, but in your note is I put it as number 3 to combine with number 4 here, to combine both here. So just make sure that you don't not confuse it. Okay. Second one is eddy current loss, which is related to resistive heating losses in the core of the transformer. So eddy current is also about resistive heating, okay, similar to the copper loss. But this one is what is inside the core. Copper loss is for the wire that we use. But the eddy current loss, it is about the material of the ferromagnetic material, which is we use like iron, for example, cobalt, okay, nickel. So that sort of material will induce eddy current inside when we do the electromagnetic induction inside the core of the ferromagnetic core. What happen is it will happen some sort of circulating current that cause the eddy current loss. Okay. And then the third one is hysteresis. So we know that hysteresis is because of the ferromagnetic materials characteristic in terms of permeability. The permeability of the ferromagnetic materials is different for several types. For different types of core, different types of the material. So it will cause the hysteresis loss because of that characteristic of the permeability of the, for example, iron or cobalt or nickel is made the core of the transformer. So that one is hysteresis loss. We have already established this also in our previous lesson as well. And then finally, the leakage flux. So the leakage flux, we have also discussed about leakage flux in the previous lesson in the real transformer, that we can represent it, the leakage flux as the primary as phi LP, and also the leakage flux at the secondary as phi LS here. So leakage flux is actually the flux that escape the core and pass through only one of the transformer winding. Okay, so it doesn't pass through that. For example, the leakage flux from primary will not go through the secondary winding. Okay, so in other way around, for the leakage flux at the secondary, it will not go to, it will not passing through the flux or core at the primary. Okay, so this leakage flux will produce something that what we call as the self-inductance. Self-inductance in the primary and the secondary coils. All right. So how do we represent the copper loss, eddy current loss, hysteresis loss, and leakage flux in terms of resistance or inductance or no capacitance? Resistance, because this is related to coil, so no capacitance, is more to the inductance based characteristics. Okay, so how do we represent copper loss? So copper loss is the loss related to heat that will be released from the transformer, meaning that it can be represented, the heat normally can be represented by resistive element. Okay, so how do we model the copper loss? We actually put the resistance, the series resistance at the at the primary and the secondary part of the transformer. Okay, and then for the leakage flux, we represent the leakage flux in terms of XP and XS. XP is the impedance or inductances at the primary side, or the accurate one is actually the XP is reactance at the primary side, and XS is the reactance at the secondary side. So this one is caused by the leakage flux at the primary and secondary side. And then we combine eddy current and hysteresis loss here. We represent this in terms of parallel branch in the equivalent circuit. but this one is refers to the core excitation effects. This is the core excitation effect that is produced by the eddy current plus the hysteresis loss. Okay, hysteresis current loss. So okay, this has already been explained. So next, I'm going to show you. First, we consider the copper loss model in terms of RP and RS, which is resistance that is replaced in series. Actually, I just move forward to show you. Actually, what I am talking about is to represent all of the components in terms of loss, copper loss, okay, copper loss, magnetizing current losses, what's the term? Core excitation effects. Actually, we are talking about this equivalence circuit that we want to represent all the losses in terms of components, electrical components. Like for this one is related to copper loss, right? Okay, this is copper loss. This is the this one is eddy current and hysteresis loss, okay, which is parallel branch. And XP and XS is the loss for the leakage flux, okay, loss for the leakage flux. So we go one by one. The first one is copper loss, which is modeled by RP and RS. For the leakage flux, as you can see from the previous lesson, we have already found this equation, which is leakage flux at the induced voltage because of the leakage flux at the primary side is equals to NP d phi LP over dt, which we has already found this in our previous lesson here. Which one? If we move on to our previous lesson, we have already talked about the leakage flux. So this equation, EP NP d phi m over dt, right? This one is the mutual inductances, but now we are talking about loss. So we are considering the second part of the equation, which is ELP equals to NP d phi LP over dt. So this is the leakage flux for primary part of the transformer. We use that equation. Next. So we use that equation, ELP equals to NP d phi LP over dt. This question actually comes from the derivation based on the Faraday's law. Okay. So similarly for the leakage flux, induced voltage due to the leakage flux at the secondary part, which is ELS equals to NS d phi LS over dt. We make this as equation 1. And then since F equals to NI equals to phi R, you know that I is proportional to phi. Then we can actually, in this case, we can represent this 1 over R is permeance. 1 over R is permeance, which is analogous to the conductance in electrical circuit. So in magnetic circuit, 1 over R is permeance. Okay, so we replace this 1 over R as permeance, which is P and I phi. Then further substitute P. Okay, we substitute P. P and I phi. Sorry, So we made this in terms of primary and secondary fluxes, leakage flux. So leakage flux at the primary is P and P IP. Leakage flux at the secondary phi LS equals to P NS IS. Okay. So we made this as equation 2. Then we substitute equation 2 into equation 1. Substitute ni. Okay. So we can substitute this, which is we substitute phi LP. So we get ELP, the induced voltage leakage, the induced voltage due to the leakage flux at the primary. We further substitute this equation and then further rearrange it. Finally, we get this pattern of the equation, which is we can represent, we can assume that this constant NP square P ni, this constant is, we can represent it as in terms of leakage inductance at the primary side. Similarly for this one, this is the leakage inductance at the secondary side. Okay, so LP is leakage inductance of the primary and LS is the leakage inductance at the secondary. So we can model this in terms of reactance. So actually in electric circuit, sometimes we call it as impedance. Impedance represent all of the R and X, R and L. R and L, we call it as impedance. Okay, so for X, X actually represents either it is inductance or capacitance. But in this case, there is no capacitance. For transformer, there is no capacitance. Most of the time, we are talking about inductance. So XP is actually LP. But for the sake of calculation, for the calculation purpose, we just write it as XP. Okay, and similarly for the secondary side, we just write it as HS, right? So, but basically, it is actually the inductance, the leakage inductance. Next is core excitation effects. So we can model the core excitation effect that which is caused by the magnetizing current IM, and also caused by the hysteresis and eddy current. Okay, so we can model IM in terms of reactance across primary voltage, which is XM, and then for IH plus E, we can model it as a resistance across primary voltage. So this is for hysteresis and eddy current loss that we release as heat. Okay, and XM represents the model of a reactance, which is magnetizing current. Okay, so for core excitation effects, we represent it as a parallel branch. All right, and then we end up into a real transformer model, which looks like this. So as you can see also in your PDF slides, this is the model of the real transformer. I redraw in my lecture notes here. Okay, so we have the series of RP plus JXP at the primary side. This represent the core loss. This one represent the leakage inductance at the primary side. This RC and JXM at the parallel branch of the circuit here represent the losses in terms of hysteresis and eddy current losses, and also the magnetizing current. Okay, and then the secondary part, we see that we have another representation in terms of resistor for the core loss at the secondary side, and also the leakage inductance at the secondary side. Okay, so as you can see, this parallel branch is also only considered at the primary side. Okay. So this is the real transformer model that considers all of the losses in terms of core loss, magnetizing current, leakage inductances, and so on. Then, okay, in our calculation, basically we want to eliminate the transformer symbol here. We want to eliminate this transformer symbol. Okay, what we do is to do the simplification. The simplification in terms of we use this turns ratio. We actually have the turns ratio. Actually, here we have the turns ratio of the transformer, which is A. So we use this A to eliminate this part. Eliminate the transformer part in this equivalent circuit, so that we can further represent it in a more simpler form without transformer, which is as you can see at the bottom of this figure. Okay, so this is the representation of the, we call it as we simplify actually. So this is the equivalent circuit referring to the primary side that we consider without transformer symbol, but we consider the equation in terms of turns ratio A. So as you can see, some of the symbols here has been changed to, for example, at the secondary part, A square RS for the core loss at the secondary. Similarly, for the reactance loss, the leakage inductance is also A square XS. And for the current, it is a little bit different to the voltage loss, which is it is 1/AIS. Okay. And for the voltage is AVS. Okay. So this is the representation of the circuit without transformer. We do much more simplification here without the transformer, considering the number of turns. Then, so in the previous circuit, in these two circuits, actually this is the exact equivalent circuit, exact equivalent circuit. But in this case, in my lecture notes, that I have my handwriting of the lecture notes here, I only draw the model, which is the model that referred to primary voltage only. Actually, in your PDF slides here, as you can see, not only the model that is referring to the primary voltage, okay, at the top one, but also the model that refers to the secondary voltage. So as you can see for the B figure here, A is actually has been used at the primary side because we are referring to the secondary part. So the secondary part of the equation remains, but the primary part we consider is with A, which is the number of turns we use for the primary part. All right. And then we can further simplify this equation, because in some situation, some of the effect can be neglected. For example, sometimes you want to avoid something that is extra branch in the calculation. Okay, so for example, in real application of the transformer, the parallel branch here, which is this parallel branch, can be neglected. So we can neglect this excitation branch because it doesn't give a much more effect, especially when we are considering a large size of the transformer. This parallel branch can be neglected because loss related to hysteresis and also the eddy current is quite low compared to the effect of the magnetizing current here, and also the core loss in the transformer. So we just can eliminate this excitation branch. For example, we have this exact equivalent circuit in the top of the figure from my handwriting notes. As you can see, this is the familiar arrangement of the exact equivalent circuit that we see in our previous lesson, in our previous slide. So we can just combine. This is one of the approximate equivalent circuit that combine, the lumped all together the resistances. For example, this resistance Rp and Rs has been combined into R equivalent P. R eq P represent the sum of the Rp and Rs. Okay. Similarly, for S eq P here represent the reactances of Xp and Xs in the exact equivalent circuit. Then, as you can see, all of the series components has been added together, combined together, so we get more simplified equivalent circuit, as you can see here. But still, in this equivalent circuit, actually, it still considers the parallel branch. So at the bottom one, we want to eliminate the parallel branch in the calculation. So we just eliminate this one into the equation at the bottom one. Okay. So this is the approximate equivalent circuit that neglect the effect of the parallel branch, which is the effect of the hysteresis and eddy current losses. So we can do this something like this. So this equivalent circuit normally applies for the transformer which is large enough, so that we can neglect some of the effects of the losses in terms of hysteresis and eddy current. Okay. So in a well-designed transformer, normally we can avoid that sort of eddy current and hysteresis loss. So that's sort of thing. So depends on the question. You might be asked to redraw or calculate all of the components in the equivalent circuit. Some equation might be asking that you have to consider the parallel branch. Some of them will not consider the parallel branch. Depends. So depends on the equation. Depends on the question. So you have to choose which equation. Which equivalent circuit that you are going to use for the calculation. So next is about open circuit test. We'll be talking about this later. Sorry for the time. Okay, so suppose that somebody should tell me if I have used others' time. We have already reached 1 minutes now, so you should go to another class. So I will finish this lecture up to this time. Okay, so we'll see you in the Wednesday for our tutorial session or lecture session. I will announce it later. Okay, we'll see you then. Okay, sampai sini saja. Because you will have to go to another class, to log into another class.
Thank you, Doktor.
Okay, sama.
Doktor,
Ya,
attendance saya kan?
nanti saya share sekejap lagi.
Okay, doktor.
Bukan, saya nak minta tolong Doktor checkkan attendance saya boleh?
Awak WhatsApp lah saya, nanti saya check.
Okay. Thank you, Doktor.
Okay.